I can safely bet that the reason why we enjoy world building is envisioning our planets, seeing what they look like. But we may not intuitively know what our planets look like. Most of the time we just tell ourselves, oh, this planet's like Mars, it's gonna look like Mars, or something like that. And a lot of the time, your planets may be so weird that you have no idea. There's no real world analog that we've ever seen before. So we go back to that central question. What does my planet look like? If you're asking yourself that question, you've came to the right place. In this video, we're going to be talking about how to get planets of every color. Starting with, black and gray objects occur when an object forms and does nothing else. No atmosphere is generated, no tectonic plates occur, no life forms, nothing. When a celestial body forms, it's going to start off as molten rock, and as that molten rock cools down, it's going to form basalt, a familiar dark gray. Examples of these dark gray objects include Mercury and the Moon. These worlds don't have any atmosphere nor plate tectonics, processes that would get rid of that old basalt. That, coupled with micrometeorite impacts and stellar radiation, are gonna contribute to a dark gray planet. I mentioned plate tectonics as a way to get rid of that basalt, but that doesn't necessarily mean any volcanic activity. Volcanic activity does indeed contribute to a dark gray surface. If you've ever been to Hawaii or Iceland, you'd know that. Another planetary example is Venus. Photos of Venus show it in a yellowish tinge, which we'll get to later. But if you somehow got rid of its atmosphere and its clouds, the surface would be gray. This is because every few hundred million years or so, the surface of Venus just sorta explodes all at once. It's relatively quiet now, but while the crust is solid, its insides are still churning, building up pressure. Once enough heat and volcanic gases are trapped, all of that pressure is going to be released. I'm sure you've heard about Yellowstone, that's going to erupt in a few somethings, however long that's going to take. Once it eventually does, it's going to cover all of its surroundings in a thick layer of basalt, as well as destroying the entire world. Now imagine that, but the whole planet. That's Venus every few hundred million years. That's very dark. So let's get brighter. Luckily, Venus is a perfect segue. We just talked about how its surface is dark gray, but from space, it's complicated. You may have seen photos of Venus in this creamy, off-whitish sort of color. Yes, that color from space is due to its intense cloud coverage, but it's not the right color. Here is a true color photo of Venus from space. As you can see, it's plain white. In fact, if you have a planet that's covered in any sort of amount of clouds, those clouds are most likely going to be white. Venusian clouds are going to be white, Earth's clouds are obviously white, Martian clouds are white, Jupiter's clouds are white. Hell, all of the gas giants that have some sort of clouds, they're white. This is due to a process called Mie scattering. Unlike Rayleigh scattering, which scatters different wavelengths of light more than others, Mie scattering scatters all wavelengths of light evenly. And since we perceive some wavelengths of light as color, all the colors combined are going to result in white. Another source of white that you may be thinking of is ice. But if you take a look at the actual icy bodies in our solar system, all the gas giant moons and all that, you'll see that a lot of them aren't white at all. Again, they're more of a gray. The only way you'd get a pure white icy body is if that ice was fresh, aka cryovolcanism. Enceladus is a perfect example. But you may also notice another little sort of hue to these bodies. A sort of brownish red. Why is that? Well, that's gonna lead us to... Okay, finally an actual color. Now here's the bit where I introduce something new to the video. This little temperature graph up here. Once an object gets hot enough, it will start glowing. The color which it glows depends on its temperature. You can use this in either one of two ways. One, if you know your star's temperature, you could figure out the color of light it emits. Any planets orbiting your star with that color will be tinted that color. Two, if your planet itself is that hot, it will glow that hot. For example, any stars that are glowing red are probably not going to be stars at all. They're either going to be really small red dwarfs at most, or brown dwarfs. If your planet itself is glowing red hot, it's probably made of lava. But how do we get a planet that's red without it being, molten? No better place to look at than Mars. And we all know why Mars is red. Rust. A long time ago, as Mars began losing its oceans, any iron particulates would have reacted with that water to create iron oxide, or rust. This red rusty dust covers all of Mars' surface as well as its entire atmosphere. But there's another way to get your atmosphere red. We're gonna bring back Rayleigh scattering. Again, Rayleigh scattering is due to how some wavelengths of light scatter more in an atmosphere than other wavelengths of light. More specifically, long wavelengths of light, like greens, blues, and violets, scatter in Earth's atmosphere well enough to cover the entire sky. Again, that's why the sky is blue. However, if your planet's atmosphere is really dense or really tall, then that blue would have scattered so much that it would just be gone, leaving behind the shorter wavelengths of light, aka the yellows, oranges, and the reds. Speaking of atmospheric gases, Jupiter! Yep, our big red boy. Its white clouds are due to ammonium crystals, same way that Earth's white clouds are due to water crystals. But the reds, we kind of don't know what they're made of yet. We kind of have some ideas, but whatever it is, that material is going to upwell from the lower cloud decks of Jupiter's atmosphere, and as it gets higher in altitude, it's going to get exposed to the sun's UV radiation, giving it its red color. Basically, Jupiter is red because it's sunburnt. Now let's go back to those icy bodies, shall we? That reddish, orangish, tannish, brownish, that's due to a material called tholins. Tholins are a solid hydrocarbon material that form way on the outskirts of a star system. They're pretty ubiquitous. Pluto has them, Pluto's moon has them, there are a bunch of dwarf planets that has them, there's an asteroid out there that has them. If you have any icy bodies in your system, there's a pretty good chance that they're gonna be tinted red because of this material. Hey, I've got a couple in my world building project that have these tholins on them. Tholins can come in a good variety, so I made one of my icy planets pink. If you think that's absurd, we have a pink dwarf planet in our solar system. Next color please. Okay, first off, the temperatures. If your star or planet is within this temperature range, it's gonna be between orange and yellow. But here's where we reach a pretty important milestone. The hottest exoplanet we have ever discovered, Kelt 9b, is around 4,000 Kelvin. That's hotter than most stars, and it's probably the hottest a planet can ever get. The reason why it's this hot is because it orbits so close to its host star. And that's gonna come with a big consequence. Its temperature and its proximity to those stellar winds is going to cause this planet to evaporate very, very quickly. Observations predict that Kelt 9b is losing between 18 and 68 Earths worth of mass every billion years. That's either more than Neptune or almost Saturn. Also, it orbits its star sideways. Any planets hotter than Kelt 9b, 4,000 Kelvin, they're probably gone already. Luckily, there are plenty of other ways to get oranges and yellows, just stick around. Sand is a pretty obvious go-to. Desert planets, they're gonna be orangish yellow. But if you've been traveling, or if you're looking up photos like I am right now, you probably already know that sand could come in a variety of colors. The color of sand is determined by the parent rock it eroded from. Sand is most commonly found as quartz crystals, which, in its purest state, comes in a form of white. Minor impurities can make it that familiar yellow that we're all used to. If it contains particles of limestone and iron, that'll cause an orange color. Add more iron, especially iron oxide, that'll turn it back to red. Volcanism is also going to play another role. If you dissolve basalt, that's going to create black sand, and ash is going to create a light gray. In super rare cases on Earth, various minerals and crystals can make beaches green and purple. Lastly, photosynthetic algae can influence the color of sand, but we're not ready for that yet. Not yet. But if you really wanted to play around, let's go back to Mars. That very fine iron oxide dust covering its surface, that pretty occasionally gets kicked up into the atmosphere, causing widespread dust storms. You could have something like that happen to your planet too, but with any color of sand that we just talked about. Another material that could get you a very rich yellow is sulfur. We've talked about how the surface of Venus is black, its clouds are white, but what gives Venus its atmosphere that yellowish tinge is a very, very tiny amount of sulfur dioxide. Jupiter's moon Io is another awesome example of yellow. Tidal forces between it and Jupiter create volcanism. That volcanism is going to spew out sulfur compounds, which are going to land on the surface. And hey, here's a fun idea. Look up a phase diagram of elemental sulfur, okay? Phase diagrams tell you if a material is going to be solid, liquid, or gas, or any other sort of weird phase, depending on temperature and an atmospheric pressure. And the states at which elemental sulfur can be a liquid is like not that crazy at all. If you wanted to, you could have a situation where a planetary object is very volcanically active, like Venus or Io, has a lot of sulfur in its atmosphere, which comes back down as sulfur rain, and create sulfur oceans. Is that viable? I don't know, sounds right to me. What's a bit more viable is something that's a bit further out in our solar system. Saturn and its moon Titan. Both Saturn and Titan are cold enough for hydrocarbons to form hazy atmospheres, giving both of them their iconic amber yellow. And funny enough, Jupiter and Saturn are made up of the exact same cloud layers. Saturn also has ammonia crystal clouds and upwelling material underneath it. The only reason why they don't look alike is because Saturn is cold enough to form hydrocarbon hazes. Jupiter is too warm. In fact, the color of a gas giant depends entirely on its temperature. In gas giants, certain molecules will only condense into colorful clouds at certain temperature ranges. And that's something we'll get to further down in the video. But for one last note of orange, if your planet has a just a little bit of nitrogen dioxide, your planet's atmosphere is gonna have a very strong orange. Green. Much like how nitrogen dioxide turns your planet's atmosphere orange, a good amount of chlorine gas is gonna make a yellowish green color. Sort of like Mountain Dew. Okay, now here's the bit you're probably all waiting for. Life. More specifically, photosynthesizers. Photosynthetic life on Earth is green because they adapted to use chlorophyll as their photopigment, the thing they use to absorb the sun's light. You may be familiar with the idea that due to different stars having different spectrums of light, planets around them that do have photosynthetic life may evolve to have different photopigments, aka photocolors, to best suit their lighting needs. But here's the thing I haven't seen anyone talk about. 1. Is there a pigment that matches that color? And 2. Is that pigment viable for photosynthesis? So, let's do a mini segment. Instead of planets of every color, we're gonna find pigments of every color. Let's go! And I'm talking like natural, biologically made pigments. If life can make it on Earth, life can make it somewhere else. Before we stray too far, did you know that there are 2 different types of chlorophyll? Chlorophyll B is gonna give us a more familiar green that leans a bit more yellow than you'd actually think. Meanwhile, chlorophyll A is gonna give us a more solid green. And in certain plants, it gives out an almost teal color. Okay, let's get crazy now. A big one is anthocyanin. This was the pigment that existed on Earth. Alright, me in the editing room here. Always a good sign to see me. If you ever hear me say something along the lines of Earth's early oceans were purple due to anthocyanins or something like that, that's just like wrong. That's straight up wrong. Earth's oceans were purple, but that's due to retinol. Retinol, not anthocyanins. Completely different pigment. I'll put corrections on screen whenever I say that. Trust that, not the stuff I said. Do your research, yeah. This was the pigment that existed on Earth before green chlorophyll dominated. And some life on Earth still uses it today. Depending on its concentration level and the surrounding pH, anthocyanins can occur blue, red, purple, pink, or black. And some plants, such as the Palestine oak and various plum trees, do use it for photosynthesis, so that's on the table. And we can't forget about carotenoids, which occur as chlorophyll breaks down, such as in deciduous leaves during the autumn or in mature lemons. These are gonna give us our oranges and yellows, and wow, okay, that was easier than I thought. Cool! Hopefully that helped, but there is a pretty low chance that your entire planet is gonna be covered by the plant color of your choice, if your planet is anything like Earth, but we can still get pretty wacky with this. If you have a gas planet in your system's habitable zone, it's normally gonna be a very bright white due to, water ice clouds, like on Earth. But if that same planet has photosynthetic life, you could imagine floating photosynthetic algae or even larger plants dominating the planet. And in order to get the most amount of sunlight, they may evolve to live above the white cloud deck, meaning that, from space, this gas planet's color will be predominantly whatever color the plants are, which is, again, whatever you want. But we're talking about green here, so let's get back to that. During the Archean period, dissolved iron in the water turned Earth's oceans green. Once photosynthesizers evolved and started creating oxygen, that iron rusted, making the oceans a blood red. Man, Earth's oceans were fucking weird back then. But we're not done talking about iron rust yet. I mentioned how many times now that Mars is red due to iron oxide rust. However, there is another infamous metal that oxidizes into a notable color. Oxidized copper is a tealish green color. Theoretically, you could have a planet like Mars covered in an oxide dust, bombarded with oxide sandstorms, but instead of a rusty red iron, this would be covered in a vibrant copper aquamarine. Unfortunately, copper is like
10,000
times less common than iron in the universe, so if you could find a way to figure that out, be my guest. I'm willing to bet that blue is gonna be the most common color a planet can be aside from monochromatic. Here's why. We've talked about all the stuff Rayleigh scattering could do, allowing blue light to scatter across the sky more than reds or oranges or yellows. And if your planet doesn't have like dust or hazes or anything like that that could tint an atmosphere, that's gonna be the default. If you want to amp that up a little, adding ozone gas will turn your skies from a sky blue to a deeper cobalt blue. Water by default is actually blue. It's not just oceans reflecting the color of the sky. So if your planet is covered in mostly or entirely ocean, then that's gonna be blue too. Unless you know iron or rust or again, Earth's oceans were weird, dude. Rayleigh scattering is gonna play a big role on gas planets too. There are certain temperature ranges a bit warmer than Earth that don't allow any clouds to condense. Those gases are still gonna be there, but it's simply too warm for them to condense into clouds. That means the appearance of that planet's gonna be predominantly based on Rayleigh scattering, aka blue. And yes, Uranus and Neptune, they're blue too, mainly because of methane hazes. And oh, look at that! Another milestone. The biggest, brightest, and hottest stars, they're gonna be blue. Whether or not they're stable enough to host planets is beyond me. But here's the thing about that blue. This blue is achieved at temperatures of around a couple of tens of thousands of degrees. Objects can get hotter than that, but that color will not change. Because of this property, this color has a name. The color of infinite temperature. Alright, I really did try, but there's nothing here, sorry. You could try combining red stuff and blue stuff, like, I don't know, an ocean planet with a red atmosphere, or a red orbiting a red star or something like that, but purple is just hard to come by, man. The only real way you could get this is through anthocyanins, which we already talked about, them making Earth's oceans purple. So I want to dedicate this segment to talking about that specifically. Phytoplankton on Earth are very powerful creatures. Despite making up only 1% of all photosynthesizers by biomass, they are responsible for almost 40% of the photosynthesis on the planet. All of it. Despite how powerful and widespread these little green guys are, Earth's oceans are still blue. Imagine just how many anthocyanin-using photosynthesizers were on Earth back in the day to turn the Earth's oceans purple. Yeah. Alright, we've lingered around the solar system for a bit too long. Let's explore some exoplanets that we've discovered that have known colors, or at least pretty inferable ones. We've talked about Kelt 9b, how that's glowing orange. A lot of exoplanets in this segment are also hot Jupiters, so let's just blaze right through them. Tres 2b, which sits around 2000K, is dark black. Dark black. Well, it's basically the void, the darkest exoplanet we have ever discovered, and that hot temperature allows it to glow a very dim red. Famously, HD 189733b is a deep blue due to the vaporized glass crystals in its atmosphere. Kappa Andromeda b and GJ504b are a reddish pink, but this one's a brown dwarf and this one's still forming, possibly also into a brown dwarf, so I'm not counting them. Helium planets like the proposed GJ436b are light gray. TRAPPIST-1b is known to have little to no atmosphere and a surface made up of ultramafic rock. If that word mafic means anything to you, volcanism, aka basalt, aka dark gray. LHS 1140b is a super-Earth orbiting inside the habitable zone of its star. Its measured mass and radius indicated a lower density than Earth, suggesting that around 10% of its mass would be water. But we would have no idea that this planet did have water, unless we have observational data to support that. And with data from the Hubble telescope and the James Webb telescope, we found evidence of an atmosphere made of nitrogen, carbon dioxide, and water vapor. There's water here. Why are we talking about this more? So we have a planet made of water inside the habitable zone of its star. That would make this an ocean world. Two things of note. One, it receives around less than half of the heat from its star as Earth does, so it's probably covered in a lot of ice too. Two, it's probably tidally locked, so the side facing the star would likely be the warmest. Probably the only region on the planet where ice isn't frozen. And considering the fact we haven't found any other gases aside from nitrogen, carbon dioxide, and water vapor here, everything on LHS 1140b is probably gonna be blue and white. White clouds in a blue sky, encompassing a blue eyeball world. That's fun and all that, but what about a planet with every color that we've talked about? all of them. Yeah, WASP 76b is yet another hot Jupiter. Its average temperature is around 2000 Kelvin, and dayside temperatures go up to 2500 Kelvin. We've also detected a bunch of vaporized heavy elements such as iron, lithium, calcium, and barium, giving it clouds of gray. The sheer amount of vaporized elements that we've discovered in WASP 76b opens it to the possibility of optical phenomena. You've seen them plenty on Earth: rainbows, sundogs, stuff like that, all caused by the way light diffracts through crystals in Earth's atmosphere. And we might have detected one on WASP 76b. An anomalous bright spot on the east side of this planet has been chalked up to a certain optical phenomena called a glory. Again, on Earth, they're pretty common on the human scale, but this is planetary. From space, you would see WASP 76b hosting rings of rainbows on its eastern side, due to the vaporized heavy elements in its atmosphere diffracting the sun's light, alongside its gray clouds and glowing red atmosphere. There's also slight evidence of this planet having a tiny little vaporizing exomoon, kind of like a hyper-Io. If that's ever confirmed, this place would truly be a sight to see. Alright, that's it. Hopefully. First of all, if I missed anything that you can think of, please put it in the comments so I could shout it out. If you want to play with this idea a little more, I have linked my own world building pack in the description of this video, which has a section dedicated to figuring out the color of a gas giant based on its atmosphere. Make a copy of it in your own drive, then you could toy with it. There's also a bunch of extra goodies in there. We'll return to the world building series probably after this video. This video is something that I've been thinking about making for like a good while, so I really hope you found it useful. If you did, like and subscribe for... Oh, fuck off. I still don't like saying that. Alright, well, just bye-bye.